Okay, so if you're having to watch this lesson from home, this is just the last problem that we'll solve for Chapter 6 on using conservation of energy with anticipated forces using inclined planes of friction. I'm going to ask you guys to draw a little sketch with me, just a picture of this. So we always start with a little diagram just to sort of help make sense of it. So if you guys will do that along with me. We have a person on a hill. And let's see, we know that the length of the hill is 75 meters. That's not the height of the hill. It's the length of the hill, 22 degrees below the horizontal. Are you guys okay with that being the same as a 22-degree hill? Angle of declination and the angle of inclination would be the same, your alternate interior angle business from your geometry days. So I like all that. That looks good. They are starting at the top of the hill, a little skiing action going on. But as is typical, skiers are able to do some work with their poles. So they're able to do some work. If you ever watch the Olympic skiers going downhill, they often push off the top there. In the beginning, they do a lot of pushing to try to add some extra energy to this. So they're able to do some work. How much work? 350. So in the process of them going down the hill, they can do that much work. What would be the speed of the skier at the very bottom? So they're going to go down this hill, and by the time they get down here, they're going to acquire some velocity. Let's go ahead and draw that here. So they got a V here. That V final is what we're looking for. Now, they pushed off the hill. My gosh, they actually start with a V initial that's not 0. So all I'm doing here is I'm making a picture of the problem, putting things that I know. It's ready for me to be able to go through and solve this. Okay. Let's see. I'm going to try to do this using energy principles. The main equation for energy principles looks like this: delta U plus delta K is equal to work non-conservative. Very powerful equation, all condensed into like 3 variables. Any changes in potential energy, any changes in kinetic energy are due to non-conservative forces doing work. Very, very powerful statement. Let's be somewhat explicit in our work here. Delta U. You guys agree there's no elastic energy, so I don't have to worry about that. It's just changes in gravitational potential energy. Where would you like to choose your reference? Where do you want your reference position to be for energy? The bottom? Let's call this our H is equal to 0. If we call that H is equal to 0, then their final gravitational potential energy is 0. That term is 0. So again, I'm being somewhat explicit in how I'm writing these things out, but that would represent the change in gravitational potential energy. I see that their change is negative. Right? They went from a high energy to a low energy position. Their kinetic energy. Now, I've been pretty consistent about writing the entire thing out so that you don't have to be like, oh, wait, why did I include it here before? Notice in this case, V initial is not 0. So I have to take into account that that's the starting energy. And so 1/2 V final, mV final squared minus 1/2 mV initial squared. My goal, you guys all see that my goal here is to solve for this, right? I'm looking, when I'm all done, I'm looking for that value. I'm looking for their speed at the bottom. Let's do the all-important right side of this equation. It's equal to work non-conservative. There's 2 things that are non-conservative that are doing work. One of them is what? One of them is the person, right? The person's doing 350 joules of positive work. The other one is what? That's doing work. Friction. And is doing negative work, correct? Okay. I'm going to draw an FBD up here. Now, you might remember when we did this kind of stuff before, we took that weight force and resolved it into two components. We took that normal force and we said that the frictional force was a fraction of that. Do you guys recall doing the FBD stuff from inclined planes and friction stuff, right? So we had to dilute the weight force. That normal force was diluted as well, and so this value and this value are the same. And then we remember that friction was equal to mu times the normal force. So a little bit of review for you on friction models. Let's go ahead and write now the work done by friction. Minus mu, which is mu sub k, that's the coefficient of kinetic friction, that's my 0.09, times the normal force. The normal force is equal to the weight force into the incline. That weight force into the incline is equal to mg multiplied by the cosine of that angle. Now, I'm not done yet. That's the frictional force. Would you guys agree that's the force of friction? Mu times the normal force? How do I turn that into work? Multiply by the 75 figures, right? There you go. Now, I'm just going to put down 75 there. Once I get this equation written, folks, do you recognize that I know every term up there except for V final? Everything up there is known except for V final. Can I cross off the mass? Is the mass of the skier important here? Can I cross it off? I don't care, they're 65 kilograms. Can I cross that off? No. Because the amount of work he does is not mass dependent. Right? So that 350 keeps that mass in that equation. Because there's no m here, I have to consider the mass of that person. Now, there's a fair amount of math to rearrange that to get to V final, right? I mean, there's a lot you got to do. You got to add mgh to both sides. You had to plug in your mu, your mass, your cosine. But it's just math. Can we agree on that? It's just math. Isolate V final and solve it. I'm going to ask. I want to see if you guys can do that. It's the algebraic side of things, and so just have at it. I'm gonna put the solution up here, but I'm not going to talk through it because there's nothing all that exciting about listening to someone describe how they're doing algebra. So I've done that before, it's really boring. So I'm going to put up the solution, you try it as well. I'm going to record it as I'm going, so if you're having to watch this from home, I encourage you to try it on your own. Solve that for V final. Okay, go, have it. I don't know if I did it right. I could have made some mistake up there, but I tried going through. Anyone getting something close to that? Okay. So there's a lot of math involved in that. It's just a lot of algebra. But my goal with that was to show you that once you write the equation using conservation of energy principles, you can streamline a lot of that complex analysis. You still have to do some mathematical work, but someone else is getting 21.2 meters per second. Okay. Again, how you do that math is completely up to you, as long as you're not violating any algebra rules and stuff like that. Some people are going to want to plug numbers into the equations beforehand, and so whatever, it doesn't matter. But just make sure that you can go through and do all that stuff and get to that final answer. All right, that's the video that I wanted to do for you on showing you how to apply conservation of energy with non-conservative forces with inclined planes and friction. Believe it or not, that is a review for you on inclined planes with friction. So just how to take that weight force, resolve it into its components, deal with that mu value, and now we can do some work done by that. I'm going to go ahead and stop this video.